In this video, we'll talk about a few common variations of how people formulate the optimization objective or regularization. Here's the optimization objective that we have been using so far, and you may have noticed that the sum is from j equals 1 to n. And so what we're doing is penalize the parameters theta 1, theta 2, and so on up to theta n, but we don't penalize the parameter theta 0 being large. So one other possible formulation, which some people use, is to use the regularization term that whereas a sum from j equals 0, right, okay, whereas a sum from j equals 0 to n of theta j squared, and this can also be written lambda theta transpose theta. It's just the end product of theta with itself. And this works to, by convention, the original version that we've been using so far is, I think, somewhat more common, but either version actually works fine, and in practice it makes relatively little difference. Another quick property of the regularization objective we're using is that j of theta, right? We can also write this as 1 over 2 sum of that squared error objective plus, and then we just take the 1 over 2m and multiply it in here, plus lambda over 2m times sum over j theta j squared. Right? Let's sum from 1 to n, say. Where notice there's this right, lambda over 2m, there's a 2m in the denominator here. There's a sense that regularization helps to prevent overfitting, and moreover, there's a sense that as the training set size m increases, we need to worry less about overfitting. So that is only if the training set size is small that we really need to worry about the algorithm overfitting, about the algorithm fitting the particular idiosyncrasies of the data set. So so the next property I would actually like to ask you to figure out, in particular, using our regularization objective. As the training set size m grows, what is the effect of the regularization term? What's the effect of the regularization? So hopefully you got that this first one is the right answer, and to explain why, we have this 1 over 2m term multiplying to lambda, and so the regularization term is lambda over 2m times sum of this, right? And so as m becomes large, as the training set size m grows, because of this 1 over 2m in the denominator, this term actually goes to 0, and so as the training set size becomes large, the effect of the regularization diminishes or decreases, and thus, the thetas will tend to, well not always, but they will generally tend to, right, and so the effective regulation term decreases, and thus the parameters will tend to increase in magnitude as the training set size grows. And this is nice because there's a sense again that as the training set size gets large, we need to worry less and less about overfitting, and thus we need less and less regularization, and this effect is naturally captured by our formulation. It turns out, just to write down the other variation, it turns out that sometimes people write down the optimization objective like this, sum from I equals 1 to m of h of x minus y squared, and sometimes people actually write so this is another variation, different formulation of the optimization objective, in which you don't multiply the 1 over 2m into lambda, and in this variation, this lambda over 2 doesn't scale with m. Of course, the only way that this and the previous formulation differ is, well, if you multiply the lambda by a factor of 1 over m, they become the same. Depending on exactly what effect you want, you can either use this formulation or the previous one that we've been using all along. But the one that we've been using all along, the one on the previous slide, is the more common one. Finally, it turns out that this form of regularization that we've been using has a name called L2 regularization, and here's why. So here's our regularization objective, and this is approximately theta transpose theta, and theta transpose theta is the L2 norm, or really the squared length of the vector theta, right? And this is approximately because I was summing from j equals 1 through n, and we're summing from j equals 0 through n, excuse me, n not n. We're summing from j equals 0, then this will be exact, but the summing from j equals 1, this is just approximate. But because this is the L2 norm, or the length of a vector, this form of regularization that we've been using so far is also called L2 norm regularization, or sometimes people also call it 2-norm regularization. And if you hear people use these names, it just means exactly what we're doing. Sometimes, and these terms I use for both the versions where you sum from j equals 0 or for the version where you sum from j equals 1. I want to very briefly mention one last version, which is sometimes you also, sometimes people will use this version, where instead of penalizing the squared values, you penalize the absolute values. And it turns out the sum of absolute values, this is also essentially the L1 norm. Oh, excuse me, I'm going to write a 1 here. This 1 superscript out here, right? And in the same place as this 2 superscript out there, this denotes the L1 norm of this vector. So, so this term here is the L1 norm of the parameter theta, of the parameter vector theta. And it turns out that if you use this optimization objective, then j of theta becomes a little more tricky to optimize, because this becomes non-differentiable. But this L1 norm regularization gets some other effects that are pretty different from L2 norm regularization, and is used for some other things. But because the optimization problem is more tricky, and because this is a less frequently used form of regularization, I'm not really going to talk about it here. But in case you ever hear people use the term L1 norm regularization, this thing here is what they mean. And whereas all the versions of what we're doing, they're called j equals 1, or sum from j equals 1, or sum from j equals 0 of this the versions of what we're doing are all loosely called L2 non-regularization methods. So that was a quick survey of a few other variations of regularization methods, and the one that we have been using all along is the most common one. In the next couple of videos, we'll take this optimization objective and figure out exactly how to apply it to a linear regression, and then we'll go to regression.